Hey everyone, so our project for reinforcement learning is humanoid locomotion. In this project, we are attempting to replicate a human motion through our project. My name is Alesha. I'm joined with my project partners, Shashwat and Sagnik. So now, why did we build this project? We built this project to develop a better understanding of the complex dynamics involved in human locomotion. The aim is to encourage the development of physiological plausible controllers for 3D human models to walk or run, following velocity commands with minimum effort. Achieving this goal would not only have an important implication for the design of more efficient and effective human-like robots, but also contribute to our understanding of the human physiology and biomechanics.
So the first environment that we chose was L2M walk. It's a complex environment that works with the muscles of the legs. The observation space is the target velocity, current velocity, and the position of the joints. And the action space is the force applied on each muscle. For the reward, they use how long there was the skeleton able to walk, as well as how forward could it move. But we were faced with an issue that this depended on OpenSim, which was not compatible with our system, and some of the algorithms were not working. So we shifted to Mujoko Humanoid V4. Mujoko is part of GIM and which has more support and more compatible to PyTorch, TensorFlow. About the environment, it's similar to L2M walk. But what it does is it does not apply force to the muscles, but to the joints. So it provides torque to the joints and see how movement works. In addition to the healthy and forward reward, we also have a control and contact negative reward. We tried three algorithms. The first one is PPO, Proximal Policy Optimization. PPO is slightly different from DeepQ, but it has similar gradient policies. The most important part of it is the clipped objective function. So what that does is, when your current policy starts deviating a lot from your last policy, the objective function clips it. So you do not deviate a lot. We trained the environment, an agent to learn the Mujoko Humanoid V4 using PPO. The max step count was good, that it was able to survive more and more and went in more than 200 steps. But the reward was not that great. And when we tried to render it, the output was not good.
So the next algorithm is the deep deterministic policy gradient. In this algorithm, basically what we do is that we train an agent in high dimensional action space to solve continuous control problems. It utilizes an actor critic architecture with an actor network learning, a deterministic policy, and a critic network evaluation action quality. The algorithm involves selecting actions based on the policy, executing them, updating networks, and employing target networks for stability. DDPG has been successful in domains like robotic control and autonomous driving by combining deep learning and deterministic policy gradients. So these are the outputs from our model. Basically, the reward was not that great and the humanoid was unable to walk, as you can see in the first and the second clip.
The third algorithm we used was NEAT, Neural Evolution of Augmenting Topologies. It is by nature a genetic algorithm. What it does is it basically defines a neural network as each individual and runs it for a lot of generations, where it modifies the weights as well as the structure of the neural network. This kind of algorithm depends on the randomness of evolution, and it leverages evolutionary techniques such as mutation, mating, and elitism. This is the outcome of the NEAT algorithm after training for a lot of generations. It does survive. It can kind of walk, but due to limited compute resources, we were unable to run it for a longer number of generations. Which brings us to the challenges. I just mentioned about the limited compute resources. NEAT algorithm requires a lot of agents running parallelly and in a lot of generations. the more number of generations you run, the better a chance evolution has a chance to learn. Algorithm compatibility was the issue that we faced with L2M. That's why we had to shift to the Mojoko environment, as well as there were problems with certain algorithms being only made for discrete environments and some were made for only continuous environments. We even had to tune a huge set of parameters for each type of algorithm, which took a lot of man hours and required a lot of trial and error. And with limited compute resources, it became a huge burden. Coming to the conclusion, extensive experiments that we have performed suggest that needs performs better in a short-term training. But to get even better performance needs a larger population, more number of generations, and it just keeps increasing exponentially the better results that you crave. But for algorithms such as DDPG and PPO, it does not give very good short-term results, but if you can train it for very, very long time, it has a better chance of obtaining a better result. So one is time scale, one depends on time scaling, and the other one depends on compute scaling. Thank you.